Prajwal, I think you can record on your system.
Yes.
You can record on your system.
I did. I started.
Okay. But I have not. Okay, recorded on this computer. Record on the cloud. Okay, you are recording. Fine. Okay. Hello and good morning, dear students. I hope you all got actually wonderful results. Yesterday, in fact, I had to call off the class because the strength was less. Today it seems to be better than what yesterday is. And I hope you all had a good time yesterday with your friends and family and enjoyed your success in the examination. Today I'll be looking at the electric potential, okay, and also the problems based on that part. In the last class on electrostatics, I had done up to Gauss theorem. But that chapter is not about only Gauss theorem, isn't it? It's also about the electric potential and the potential energy. So today we will discuss about the electric potential energy and potential, both put together. Some very interesting problems generally are done here. And a lot of questions which come in the electrostatics will be on the potential, especially in the KCET. You will find that there will be many questions on the potential part. Okay, problems are easy to do and you can easily score marks in this. Also, you will find that the potential energy part and other things will be used in your mains examination and NEET. So together will form a very important part of your, say, examination curriculum. So let's start with the synopsis, look at all the important ideas. I will first of all look at the electric potential energy. Okay. Now, what is this electric potential energy basically is about? If we consider two charges, Q1 and Q2, then the potential energy is always defined as the work done against the electrostatic force. This is in fact is what the potential energy is about. If there are two charges, Q1 and Q2, separated by a distance r, then we all know that the potential energy of the system will be equal to K Q1 Q2 by r. It's just the dependence on this. Okay. Now, if you plot a graph of U versus R, you will in fact be getting a curve like this. You will find that the potential energy will be 0 for R equals infinity. And similarly, potential energy will be infinity for R equals 0. Now, if you have the two charges, one positive and another one negative, okay, then the potential energy will be written as minus K Q1 Q2 by R. The negative sign always indicates that the electrostatic force itself will do the work. And therefore, the system is losing energy. That is what the negative sign is indicating, because the system is losing energy because the work is done by its own force. Okay, if you do against it, then you will have the force to be always positive. Now, an important point to note here is, and that is this point is, if you have, say, more charges, if you have more than 2 charges in the assembly, then the total potential energy will be given as half of summation of K Qi Qf divided by Rif, where I and F will not be same. That is the only condition you have. Other than that, they both can actually have value from 1 to n. So if you have n number of charges, this is how you find out the total potential energy as. If you all have written down this, I'll go to my next page. Can I go to my next page? I think Prajwal, we can allow them to unmute the students. Okay, I have now allowed you all to unmute whenever you have questions, whenever you have queries. So please unmute and then answer me now. Can I go to my next page? Is it all right? Next idea?
Yes, sir.
Okay, thank you.
Yes, sir.
Thank you.
Yes, sir.
The second point is the work done can also be written as the change in potential energy. There are some very interesting problems done on this case. I'd just like to do one of them. If I have 3 charges here of charge Q and side A, on which on the triangle of side A, the charges are placed. Now the question is, what is the work done in making these charges be at a triangle of separation 2A. It was A here, no? 2A, the same charge. So to transform from this triangle to this triangle, what is the work done required? What is the work to be done? So that work done can always be written as delta U, the change in the potential energy, UF minus UI. Now the question is, what is UF, what is UI? Now UF can be written as K, okay, QQ by 2A for these 2 charges, plus K QQ by 2A for the next set of charges. Finally, for the last set of charges, it is K QQ. So this is the initial potential energy minus this is the final kinetic potential energy. Now the initial potential energy will be again K QQ by A, not 2A now, A, because that is the initial state, plus K QQ by A plus K QQ by A. Now you'll be saying that I could have written this as simply 3KQ square by 2A, you're right, minus KQ square by A. So what do you get the, therefore the answer to be is minus, this also is 3 by the way, this also is 3, is minus 3 by 2 KQ square by A, KQ square by A. And I have a negative sign here for the work done. Whenever you have negative sign for the work done, it means that you don't have to do the work. The work will again be done by the system. It's a repulsive system. All the charges are repulsing. So on its own, it wants to expand to a triangle of 2A. Okay, and that's what the negative sign is indicating. Okay, so I'll go on to my next idea in this. If you all are done with this, can I go to my next idea in the potential energy part?
Yeah.
Okay. Now, another idea here in the potential energy part is the relation between force and potential energy. F is given to be minus du by dx. I think this is a very well-known relation for all of you, which says force is the negative potential gradient. This itself was asked in many examination. What do you say force as? Force basically can be written as negative potential gradient of of potential energy. Hey, you should at least make sure that no one disturbs you, or keep your mic say switched off. Otherwise, you'll be disturbing everyone in the class. Okay? Or in general, this can be written as minus du by dx I cap minus du by dy j cap minus du by dz k cap. Okay, this is what in fact the force can be written as a general expression. The last point in the potential energy would be use of conservation of energy in electrostatics.
Excuse me, sir.
Yeah, tell me, please.
So isn't it minus dV by dx?
Minus?
In the previous formula for the force. Isn't it minus dV by dx?
Okay. Maybe I should tell you that here. I had mentioned it in the previous class. Electric field is what is minus dV by dx. All right. Where V is the potential. All right. But here U is minus du by dx, where U is the potential energy. Do you know the difference between the two, potential and potential energy?
Sure.
Huh? Do you know the difference between the two?
Yes, sir.
Potential energy is related to the force. Potential is related to the electric field. All right. Potential is potential energy divided by unit charge. Potential energy per unit charge is what we call it as potential. All right. Potential is related to electric field. Potential energy is related to the force. Okay. It's du by dx. That's the right one. Did you follow that?
Yes, sir.
Okay. Now there can be a lot of problems asked also on the conservation of energy. Now, what kind of problems do come? Okay, we'll take an example and illustrate. Okay, consider that there is a charge Q fixed at O. Okay, like this. A charge Q is fixed at O. Okay, another charge Q is projected with velocity v from a very large distance. My dear students, I would like to say that in the lectures that I always have, you will find a lot of these kinds of problem types, which will help you to solve the MCQs later very easily. Okay, please pay attention and then try to actually know this. So I have another charge Q, which I'm going to project it with a velocity v, like as shown in the figure in this way. Now this distance initially is very, very large. Whenever I say a very large distance, you take this r to be equal to infinity. That's what actually in physics means. Very large means you can take that r to be, in fact, infinity. So now I'm going to consider that this will be projected. Now the question, find the closest distance of approach. Now, what does it mean? What is it that we are looking at? You have this coming here, and as it comes closer and closer and closer to this, the potential energy keeps on increasing. Now, when it comes to a point here, all the kinetic energy would have got converted to potential energy, and the velocity at this point will become 0. Now, this distance, in fact, is what I call it as the minimum distance of approach. We have to find out what that minimum distance of approach is going to be. Okay. Now, how do we solve a problem like this? I can use the concept of conservation of energy. Take this as the initial point. Take this as the final point. Now at the initial point, the potential energy will be equal to KQQ by R, but R is infinity, isn't it? R is infinity, and therefore 1 by infinity will become 0. But the initial kinetic energy will be given as half mv square, where m is the mass of this particle, half mv square. Finally, when it comes to this point, the potential energy will be equal to KQQ by d, the minimum distance that we have to find. No, that d is here. But whereas the final kinetic energy is equal to 0 because the particle has come to rest momentarily. After that, of course, it's going to actually return back. So the particle will come here, momentarily it will be at rest, and then after that it returns back. It returns back. So this is the closest distance of approach. Closest distance of approach. Now I can now say that ui plus ki is equal to uf plus kf. Now what will that turn out to be? Look at it. First term is 0, and then second term is half mv square. On the right hand side, I have KQQ by d, and the second term is 0. Now from here, I can easily obtain the relation for d. So I get this to be half mv square is equal to KQQ by d square. So this is how I always obtain the minimum distance of approach. Minimum distance of approach. Okay, this is the expression for the minimum distance of approach. A very important part of problem. You can have many variations of this. You'll be getting in different MCQs. Okay, in a different exam, different parts will be actually asked. They may ask you to find V, they may ask you to find D, and so on and so forth. If you're all done with, I'll go to my next part. Can I go to my next part?
Yes, sir.
Yes, sir.
Next part is the concepts of electric potential. So someone in fact had a confusion about it. So it's good that we need to actually discuss about this potential. It is defined as potential energy per unit charge. Okay, that is V will be equal to U divided by Q naught. U divided by Q naught. This is something similar to electric field, which was defined as F by Q naught. F by Q naught. So potential will be related to the electric field, therefore. Okay, so this is how, in fact, one can define this as. Now, obviously, how do we also define in terms of work done? So potential is defined as the work done in bringing a unit positive charge from infinity to a point. Okay, and that in fact is called the potential. Unit positive from infinity to this. So what will be the potential because of different configurations? So let us look at that. Potential due to a point charge. Due to a point charge. If you have a point charge here, then the potential at a distance r will be given as kq by r, isn't it? And if you have a minus charge being kept here, then the potential at this point will be equal to minus kq by r. Minus kq by r. Minus kq by r. So please make a note. Negative charge will produce negative potential. Okay, for a negative charge. Now, what happens if you have multiple point charges? Multiple point charges. That is, you have large number of collection of problems, collection of charges. Q1, Q2, Q3, and Q4 like this. So at a particular point here, if you know what is the distance of each of them is, okay, then you can find out the potential at this point quite easily. Let's make one of them as minus, okay, minus. Then the total potential will be simply V1 plus V2 plus V3 plus V4, okay? Or in general, you can say potential will be equal to summation of all the potentials due to the individual charges. So you will therefore find that the potential in this case will be equal to K Q1 by R1 plus K Q2 by R2 minus K Q3 by R3, because there's a minus charge there, plus K Q4 by R4. So this is how you find out the potential because of multiple charges. And you will find a lot of questions to be will be asked on this multiple charges. They'll be given in different configuration. Like for example, this. I will not work out this problem. I will do it later. It anyway there in the question later on. K Q1, Q2, Q3, and Q4 are charged, let us say, which is placed on a square of distance A. You have to find out what is the potential at O, what is the potential at P. Okay, so for finding the potential at O, find out what is K Q1 by, this is X, Q1 by X, then K Q2 by X, K Q3 by X, K Q4 by X, and find out what is the net potential is, and do this. So the question generally asks this: find potential at O and at P. Another very interesting question would be find the potential difference between O and P. This is a very, very interesting question. Delta V will be equal to Vp minus Vo. So you'll have to find out what is the potential difference between the two. This is an interesting problem also. We'll work out the problem later. We'll not worry about it right now. But this is an important type of problem that you will be coming across. So if you're all okay with this, can I go to my next idea?
Yes, sir.
Okay.
Yes, sir.
Thank you.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Let's see what is the potential due to an infinite charged rod. Okay, I have an infinite charged rod here having charge Q, and you have this like this, the distance R. Then the potential will be equal to 2k lambda into log R. Here V is taken to be 0 at R equals 1 meter. So this is an information that you should always know. Okay, this is where lambda is the charge per unit length of this rod. Now let's find out what is the potential due to a charged ring, okay, at a point on its axis. You all understand what actually a charged ring is. Okay, this is the ring that I have chosen, and this ring basically has okay, something like this here, and there's a charge on the ring. Okay, there was some student who really was creating this issue. I said, why do you do that? I mean, I told you to switch off the mic. I do it myself. I try to mute it, and you still unmute and then create the disturbance. Huh? Now I want to find out what is the potential at a distance x, and the radius, let us take it as r. Then at this point, the potential can be shown to be kq by root of r square plus x square, r square plus x square. Okay, you'll find that at x equals 0, the potential is given to be kq by r. Very interesting. The total charge is q and is given by kq by r. Now, keep this as your reference. Electric field in this case was 0 at the center. So electric field is 0, but the potential is not 0. So keep in mind, you can have this particular case. Okay, we can have electric field to be 0, but potential need not be 0. This again is a very important question that is generally asked. So keep in mind, this is marked as an important point there. Okay, so now I think I'll go to my next page to illustrate one more concept here, the potential. Prajwal.
Yes.
I think we need to do something for this. You need to be quick in actually admitting the students. Otherwise, it keeps coming here, and then it's actually a disturbance for the board. Okay. So immediately do it. Immediately admit them, and I think we'll do it for another 5-4 minutes, and then after that we'll lock the book.
Yes. Okay.
Thank you. Now, for the fifth case is the electric potential due to someone is asking me to show the ring formula again. Okay, please be careful. Please be quick, and then I want you to don't keep bothering, because we have a lot of things to do in this chapter. See, look, I will again allow you to actually unmute, but I want you to be more responsible. All right. So you can unmute and ask me questions if you have any, because it's very difficult to see the chat every time. So, but maybe be responsible. Okay. Don't keep it on and then make some kind of noise in the background. Potential due to a charged shell. Due to a charged shell. We have seen this in the gravitation, very similar problem. Okay, you have a shell and it is charged now. It is charged. And I want to find out what is the potential inside. Okay, at a distance r. At a distance r. So the potential inside will be given by kq by capital R. So anywhere inside, the potential is same. Same for all points inside the shell. Okay. Now on the surface will also be equal to kq by r. But at a point outside, the potential will be given by kq by small r. Kq by small r. So if you plot a graph of potential versus r, you will get something interesting here. It will be same until you have small r equal to capital R, and after that it reduces like this as 1 by r dependence. So this will be your kq by r. Okay, please mute your mic. If you do not even have the Shivank, mute your mic. Mayur, mute your mic. You should at least have that sense, no?
Now,
You don't know what
putting
I'm
him
telling you,
to,
but still you do the same thing.
I'll put him into waiting room now.
No, don't do all that.
Okay.
Don't do all that. Okay, now I have actually a solid charged sphere. Now in this case, what will be the potential at different points? So radius of this, let us take it as r, and I want to find out what is the potential at the distance r here inside. Okay, you will find that the potential inside will actually be having a relation like this: kq by 2r cube into 3r square minus r square. Okay, very interesting. Inside, so a solid sphere is given with this. Okay, on the surface, this will be kq by capital R. At the outside point, this will be equal to kq by small r, where this in fact is the distance r. So it's given by kq by small r. This is the potential outside. So what we have done is we have looked at the potential due to different configurations. All right. If you all have done with this, I'll go to my next page.
Excuse me, sir.
Yeah, please tell me.
What will be the electric field in this case?
Okay, you didn't attend my previous classes, right? The electric field inside will be KQR by R cube. Okay, inside. Electric field outside will be KQ by R square. Electric field on the surface will be KQ by capital R square. Okay. Is it okay? Sri Lakshmi is the one who asked me, is it? Is it all right?
Yes, sir.
Okay. Now, let us go to the relation between electric field and potential. We talked about the force and the potential energy there. Here we'll talk about relation between electric field and potential. Electric field, in fact, is given as minus dV by dx I cap minus dV by dy j cap minus dV by dz k cap. Okay, or in other words, you can also say that this electric field can be written as minus dV by dr, where electric field will be called as the negative potential gradient. Earlier it was potential energy gradient, right? Force is potential energy gradient. This is potential gradient. Okay, that's the point to be. Okay, yes. Now, you will always find that whenever electric field is zero, potential will not be zero, but potential will be constant. Whenever electric field is zero, then it means dV is equal to zero. Okay, what would that imply? That would imply that the potential is constant in that particular region, Okay, now some examples basically will be helpful here. If you consider a uniform electric field like this, then the potential at this point, maybe call this as 1 and this point as 2. So this will be V1 and V2. The separation between them, let us take it as delta X. If the electric field is E, then it can be shown that this electric field E can be written as minus V2 minus V1 divided by delta X. In other words, electric field can be written as V1 minus V2 by delta X. And also it can be shown that V1 will be greater than V2. And the potential decreases in the direction of electric field. Okay, it decreases in the direction of electric field. That is what in fact is the idea of this whole thing. Okay, that is the relation between electric field and potential. If you all have done with this, I'll go to my next page. Have you all written down this?
No, sir.
Okay.
1 second, sir.
Yeah. Okay, so I'll go to my the last maybe last 2-3 ideas. So after that we can start solving problems. Okay. The next one is called as the equipotential surfaces. Now the surfaces where the potential at all points on the surface is equal, then it's called as an equipotential surface. Okay, there are plenty of examples for this equipotential surface. So let me try to give it for different cases. Now for the first one, I'll say for a point charge. If you have a point charge, then you will find that at any distance r from this point, the potential will be same, not just 2-dimensionally, but also 3-dimensionally. Therefore, on the surface of a sphere of radius r, the potential will be same at all points. Okay, so sorry. If I take this as V1, the potential at any point here will be same, will be V1 itself. And therefore, this will be called as an equipotential surface. Now you will find that even this also will be an equipotential surface. But only thing is here, this distance will be some r dash. So this will be now V2, or maybe you can call this as R2 and this is R1, R2. So potential at any point here will be V2. This also will be an equipotential surface. For that matter, you consider another sphere here like this. This also will be an equipotential surface, but this may be at V3. And therefore, you can say that all concentric spheres will be equipotential surface. All right. So that is in fact is the idea behind this. You will find there are some important points to note for an equipotential surface. Number one, electric field will be perpendicular to the equipotential surface. Look at this itself. Electric field will always be radially outward. So at any point here, the electric field will be perpendicular to this surface. So here also in this direction, electric field is like this. So at any point you consider, it will be perpendicular. So electric field will be perpendicular to an equipotential surface. Tangential field will be 0 in this case. Now this is for a point charge. Now what about if you have a charge distribution like this, which is a line charge, then you will find that if you consider a cylinder of radius r around this, then the cylinder will be an equipotential surface for this case. So you consider any number of cylinders here, they'll all be equipotential surfaces. So this one will be an equipotential surface. Though they will have different voltages. This may be at V1, this may be at V2. But all points on this will be at the same potential. So similarly, if the electric field is uniform, like this, okay, then the equipotential surface will be the planes perpendicular to that. All planes perpendicular to the electric field will be equipotential surfaces. So this will be an equipotential surface. Here also you can see that the electric field will be perpendicular to this. A very important idea. We'll be using this in the problem solving later on. Okay. If you all are okay, I would like to go to my last item of discussion. This is about conducting shells. Okay, I'll be able to only give you some of the ideas here. I can't really go into the details of all of them. If you have a conducting shell of radius r, then the charges always reside on the outer surface like this. Even if it is a solid conductor, this is what in fact the case is. Now for this, we all know that the potential is going to be kq by r for a point inside, and v will be equal to kq by capital R if it is on the surface, and it will be equal to kq by small r if it is outside the surface. Now what we'll do is we will consider two such, say, conductors. Now these conductors in fact are concentric. One of radius A, the other one of radius B. Now for the inner one, let me give a charge Q1. For the outer one, let me give a charge Q2. Then I want to find out what is the potential, okay, on A, that is the inner shell. The potential on A can be shown as KQ1 by A plus KQ2 by B. Similarly, potential at A, at this point B here, can also be written as KQ1 by B plus KQ2 by B. Okay, this is the expression for VA and VB. This is called as concentric shells. So this is the expression for those two. Now the another question that they keep asking you is, what will be the difference in the potential between the two? So this is called as a potential difference. Now what will that be equal to? Will be equal to KQ1 by A minus KQ1 by B, or will be equal to KQ1 into 1 by A minus 1 by B. This is the potential difference between the two shells. Okay, a very important idea. You will be asked a lot of things on this pattern. Now the same expression can also be written in terms of surface charge density. Okay, the same expression, same thing can be expressed in terms of the surface charge density, where inner one, let us say, has sigma 1, which will be equal to q1 divided by 4 pi a square. Similarly, the outer one is having q2 by 4 pi b square. I'll call that as sigma 2. Now, what will be the expression for VA now in terms of the sigma? Okay, wherever you have q1, substitute for sigma. By B. So therefore, you'll get this to be, and remember, K is 1 by 4 pi epsilon naught. So 4 pi also will cancel off, and hence you can show that this will be simply equal to sigma by sigma 1 epsilon naught into A plus sigma 2 by epsilon naught into B. This will be your VA. So it's much more easier to write down the expression for VA in terms of the sigma. Okay. Similarly, what will be VB? VB will be equal to K sigma 1 into 4 pi a square divided by B plus K sigma 2 4 pi b square divided by B. So you can also write this as sigma 1 by epsilon naught a square by B plus sigma 2, okay, B by epsilon naught. So this is another way of writing VB. So I can write down the expression for VA and VB in terms of sigma as well. So this will be very useful. So please make a note of it. I'm going to my next page. If you all have written down this, okay, I'll go to my next page. Can I go to my next page?
Yes, sir.
Yes, sir.
Karthik, can you please switch off your mic? Yeah, this is called as the grounded conductors. Now, grounding is a very interesting phenomenon. If you take a conductor and then connect that to ground, then what happens is the potential of the conductor and the potential of the earth of the conductor, they both will become same. But what is the potential of the earth taken as? Potential of the earth is always taken as 0. Therefore, whenever you connect actually a wire to the conductor, then what happens is the potential will become 0. So the net potential there has to be 0. So that is precisely what is going to happen now. So if you consider two concentric shells where there's a charge Q given on this, radius is A, Q is the charge, and the outside is simply connected to the ground. You will find that because of the induction effects, there will be a minus charge induced on this part. Outside positive charge are all gone to the ground, and hence you can't really have any positive charge outside, they're all gone to ground. In this case, what will be the potential of A? It can be shown that the potential at A can be QK by A minus KQ by B. That of the B will be 0 because of the reason I told you. It's connected to the ground, isn't it? And therefore, VB will be 0. So what is the potential difference, therefore, is KQ into 1 by A minus 1 by B. This is for a conductor which is grounded in this way. Now I can also consider another case where you will have charge on the outside conductor and the inner one is connected to the ground. The moment the inner one is connected to the ground, VA here will be 0. So VA will be 0. But you can show that VB will be equal to KQ by B square into B by A. The reason being that there'll be some amount of charge on this as well. There'll be a negative charge on this inner one. And that negative charge can be shown to be equal to minus K minus Q A by Q into A by B. Minus Q into A by B. Okay, that is the amount of charge that will be coming from the ground onto this shell. So this is another expression here that you will need. Okay, so I think with this I've come to the end of all the important ideas I wanted to tell you in the potential and the potential energy. So let us now start solving problems on this idea. I will be sending this also a little later, but now please keep this as a reference for your problem solving. Okay, number one. Pay attention, a very important part here. Someone is asking me something. I didn't get your question, Sakshi. Sir, why not QB? What is QB? What is QB? I didn't get your question. Okay. Now let's solve first one. In a uniform
Sir, how QA, why not QB, sir? Sir, how QA is equal to minus QA by B? Sir, why not QB?
Okay. I'm not really deriving the expression, but if you insist, I can always show you why it is so. See, before connecting to the ground, there was no charge on A. So the charge came only because of grounding. Okay. So let us say charge is QA here. I must have QA by A, okay, plus KQ by B, the charge that is given on this QB should be equal to 0 because it's connected to ground. Now, if you solve this equation, you get this to be QA by A is equal to minus Q by B. Am I right? And therefore, what is the charge on the inner one? QA is equal to minus QA by B. And that is why it is A by B and not B by A. Is that clear?
Yes, sir.
Okay. A uniform electric field, the potential is 10 volts at the origin of a coordinates and 8 volts at each of the points 1, 0, 0, 0, 1, 0, 0, 0, 1. The potential at point 1, 1, 1 will be a very nice question. Okay. Now, the way that I'm going to solve this problem is to write down the potential difference as integral of, okay, you can say minus Ex dx plus integral of Ey dy. This also is minus, I'm so sorry. Minus of integral Ez dz. Okay. Now, the electric field basically, the potential difference has to be obtained. And what have they given us? The uniform electric field, the potential is 10 volts at the origin of coordinates 8 volts. And 8 volts at the points 1, 1, 1. The potential at 1, 1, 1 is to be obtained now. Okay. So what I'll do is, the potentials are given. Potentials are given. Okay, fine. I think I'll go the other way around. Potentials are given here at these 2 points. Okay, along the x direction. So let me take this as origin. Look at this point 1, 0, 0. Where is 1, 0, 0? It's on the x-axis. It's at this point. The potential difference is 10 volts here and 8 volts here. Now you can immediately say that there must be an electric field here in this direction. And this electric field must be given as 10 minus 8 divided by what is the distance between the two is 1 meter according to this problem. And therefore, this should be equal to 2 Newton per coulomb. So Ex, I'll call it as Ex. Similarly, if you also look at the another point, the potential is 8 volts at 0, 1, 0. Now, where is 0, 1, 0? It's on the y-axis. Am I right? It's on the y-axis. Here also it is 8 volts extension. So there must be an electric field along y direction as well. That will be equal to 10 minus 8 divided by 1 also to be equal to 2 Newton per coulomb. In what direction is it? In what direction is it? It should always be from the higher potential to the lower potential. So electric field is along the y direction. Same way. Along the z direction, also it is 8 volts. And what is the electric field there given by? Is given by 2 volts. Same idea. 2 Newton per coulomb. 2 Newton per coulomb. So I have therefore electric field in all directions for this problem. In all the directions. Now they're asking me to find out what will be the potential difference between the origin and 1, 1, 1. Now this can be written as I told you, delta V can be written as minus Ex delta X minus Ey delta Y minus Ez delta Z. All right, this is what in fact I get this to be. Now I have got the electric fields are all in this particular direction. So I'll be getting this as minus 2 into. Now what is the distance along the x direction is 1. Take it as minus 1. So then I'll have 2 and then minus 1 for the delta y. Then similarly for delta z also it is minus 1. So what is the voltage therefore that I have basically will be 2 plus 2 plus 2 will be equal to 6 volts. So this will be equal to 6 volts. What is the potential difference between the origin and this point is 6 volts. So you have this point here is origin, another point here 1, 1, 1. The potential difference is given to be 6 volts. But what is it that you want to find? You want to find out what is the potential at this point. Okay, I'll call this point as P. So you have to find out P. So now you will say that this is at 10 volts. These are 10 volts. And all the electric field will be in this particular direction. So it should be lesser. So it should be, so VP should be equal to 10 minus delta V. Now 10 minus delta V is therefore 4 volts. So the answer to this question therefore is 4 volts. A very interesting idea on the electric field and the potential difference. On the electric field and the potential difference. Am I clear? Is it okay for all of you? How I got this as 6 volts is because there is a potential difference coming in all directions, X, Y, and Z. And therefore the potential at that point will be 6 volts. Will be 6 volts. Okay. Why minus 1? Correct. That's a nice question. Why minus 1? See, my initial point is 0. Final point is 1. Okay. And therefore, what is the difference? It should be 1, 0 minus 1. And hence I get that to be minus 1. Okay. Because I'm always considering V origin minus VP. So my initial point will be 0. Final point will be minus 1. And hence I get that to be this. A point charge is surrounded symmetrically by 6 identical charges at distance r, as shown in the figure. How much work is done by the forces of electrostatic repulsion when a point charge q at the center is removed to infinity? So initially the point is here, okay, q. Okay, here. From here, I have to move up to infinity. Now, dear students, the work done can always be written as delta Q, or it can be written as Q naught into delta V. That also is another way of writing it. So here I can write it as Q naught into VF minus VI. Now, where the potential at the infinite point, because it's at infinity, isn't it? VF is at infinity. That should be equal to 0 because potential at infinity is always 0. Now, what is the potential that we have at the center? Okay, VI is at the center. So VI will be equal to KQ by R, and there are 6 such charges. So each one is contributing KQ by R. So there are 1, 2, 3, 4, 5, and 6. So 6 charges are there. And hence I get the total potential there to be 6 KQ by R. 6 KQ by R. Now the work done. Work done will be equal to Q naught into 0 minus 6 KQ by R. KQ by R. This will be minus 6K Q square, because Q naught also is equal to Q in the problem, divided by R. What is K? K is 1 by 4 pi epsilon naught, and therefore I get this to be by R. Look at the from this, I think you can pick the answer quite easily. It should be 6 Q square by 4 pi epsilon naught R. Okay, they are not really worried about the negative sign because none of them in fact have negative sign. If you had an option of negative sign, please choose that negative sign. But here the best option is 6 Q square by 4 pi epsilon naught. That's the most appropriate one that I can think of. Okay, problem number 3. When a body is earth connected, electrons flow from the body to earth. This means that the body is okay. See, connected. Electrons flow from the body to earth. So when does actually electron flow from body to earth? When there is excess electrons. Whenever there is excess electron, then it must be negatively charged. Negatively charged. So therefore, the option for the third question is that should be charged negative. Charged negative, because electron is flowing from earth to body to the earth, from the body to the earth. If it had been other way around, where the electrons would go from earth to this, then the earlier charge basically was positively charged. This also can be for the another question. So this is essentially for another case. Okay. If you all are okay with this, I'll go to my next page.
Yes, sir.
Question number 4. Charges of 10 by 3 into 10 to the power minus 9 coulomb are placed at each of the 4 corners of a square of side 8 centimeter. The potential at the intersection of the diagonals is, okay, interesting one. So you have to find out what will be the potential at this point. So take this to be like a square. That's what they have told you. Okay, and what is the side of each of them? 8 centimeter. Now the intersection of the diagonal is the center of this, right? If I call this as x, you all can immediately see that x will be equal to 8 divided by root 2. Yeah, 8 divided by root 2. So this can be written as 8 by root 2 can be written as 2, so 4 root 2. Another way of writing it is 4 root 2. Or you can retain it as 8 by root 2. It's also fine. I think you can retain it as 8 by root 2. Because if I look at the option, that's what it's turning out to be. Now the charge on each of them is identical. Okay, and therefore the potential at the center will be 4kq by x. 4kq by x. So hence I'll get this to be 4 into 9 into 10 to the power 9 into q. Q is given to be 10 by 3 nanocoulomb. Very good. Good for us. 10 by 3 into 10 to the power minus 9, because the minus 9 will cancel off. No? So that's why it's useful. Then this will be 8 by root 2. 4 ones are 4 twos are. Okay. 3 ones are 3 threes are. So I get this V to be therefore 30. So there is 1 2 here. No, 1 2 here. So this will be 30 by 2 is 15 root 2 into 10 to the power minus 9 cancels off. Isn't it? I forgot the centimeter. So into 10 to the power minus 2. So goes up, becomes 10 to the power plus 2. So therefore this should be 1500 root 2 volts. So just see if there's an answer like that. Okay, the answer to this therefore is the second one, which is 1500 root 2. Okay. Now coming to the next question. Again, a very nice one, and lot of times you will find this question coming up. I think this actually had appeared in one of the mains examination or the NEET examination. Okay, I picked it up from that. In a rectangle shown, two corners have charge -5 microcoulomb and 2 microcoulomb. The work done in moving a charge of 3 microcoulomb from point B to A is given to me. So from B to A, I need to actually move this. So what are the distances here? This is 15 centimeter, this is 5 centimeter. So from B to A, isn't it? From B to A. See, whenever it is moved from the point B to A, take this as the initial point, take this as the final point. Work done is always, then you will have less confusion with the signs, will be always Q naught into
ಫಿಸಿಕ್ಸ್ ಮಾಡ್ತಾ ಸ್ವಲ್ಪ ನೋಡ್ಬೇಕು ಬಯಾಲಜಿ ಚೆನ್ನಾಗಿರ್ತದೆ ಅಂದ್ರೆ
will be VF minus VI. VF minus VI. So VF is the final point. In this case, this has to be therefore VA minus VB. That will be the work done. Okay, let's see what VA is. VA is KQ1 by 15. Okay, KQ1 by 15 plus KQ2 by 5. These are all centimeters. So you will say into 10 to the power -2, isn't it? Into 10 to the power -2 here. So take this into account. So I can therefore say VA will be equal to K, which is 9 into 10 power 9 divided by 15. There's a minus sign now, so be careful. I'll put a minus sign here because it's -5, isn't it? Into 5. Okay, plus K. This is other one is 2 microcoulomb charge. So 9 into 10 power 9 into 2 into 10 to the power 5 into 10 to the power -6 also is write down. 2 into 10 to the power -6 divided by 5. Don't forget 10 to the power -2 for both of them. So you will get VA therefore to be equal to 9 into 10 to the power 9 into 10 to the power -6 divided by 10 to the power -2 into -5 by 15, okay, plus 2 by 5. 2 by 5. So this is 5 by 15 can be written as 5 ones are, 5 threes are, right? 5 threes are. And hence the simplification has to be worked out here itself. So VA will turn out to be 9, 10 to the power -3. So this becomes 10 to the power +3 here. 3 plus 2, 5. So 9 into 10 to the power 5, 10 to the power 5 into 2 by 5 minus 1 by 3. Minus 1 by 3. Simplify this further and keep it with you. So this will be 6 minus 5. 6 minus 5 will be 1. 1 divided by 15. So 9 by 15. 9 by 15 into 10 to the power 5 volts is VA. Now, similarly, one has to also work out VB. VB will be equal to, look at it, for VB, the charge -5 is at a smaller distance, right? And therefore, I get this to be K. I'll take out K outside, so that becomes easy for you to write down now. -5 into 10 to the power -6 divided by 5 into 10 to the power -2 plus 2 into 10 to the power -6 divided by 15 into 10 to the power -2. Okay, the charges here. No potential will be produced by these two charges at this point. So this will be 9 into 10 to the power 9 into, you can also take out the powers outside, -6 divided by 10 to the power 2 into -1 plus 2 by 15. 2 by 15. So what is the answer that you get therefore will be equal to 9 into 10 to the power 5. Okay, 15 minus 15 plus 2. Minus 15 plus 2 will be minus 13 by 15. Minus 13 by 15. This is what your VB will be equal to. VB will be equal to. Very interesting one. So you will therefore find that I have to find the difference between the two, isn't it? That's what the whole problem is about. So you have to find out the work done. which will be Q naught into V A minus VB. Now Q naught is 3 into 10 to the power minus 6. VA is 9 by 15 into 10 to the power 5. Minus, you have one more minus sign here. So that is 13 into 9 into 10 to the power 5 divided by 15. I didn't simplify that for a reason. Okay, now I can do it easily. So 3 by 15 into 10 to the power minus 1 into 9 also I can take it outside. So I'll have this to be equal to 1 minus 13. So which will be equal to 9 into, so this is turning out to be plus, minus of minus becomes plus, I'm so sorry, plus. So this will be 14 by 5, 14 by 5 into 10 to the power minus 1. Simplify this and you should get the answer for the work done. Okay, quite a lot of things to be done, but can't help. This is how you can actually work out. And then find out that that this will turn out to be for the fifth one, the answer turns out to be 2.8 joules. 2.8 joules. Simplification is there, can't help. This is of a little higher order, but it's not a tough problem, it's a lengthy problem. Okay, and you may have actually these kinds of lengthy problems, especially in the mains examination. Okay, CET also sometimes they can always ask. An electron is traveling from infinity with a velocity v into an electric field due to two stationary electrons separated by a distance of 2 meters. Okay, it comes to rest when it reaches the midpoint of the line joining the stationary electrons. The initial velocity of the electron is a nice question, very nicely can be done. We had actually looked at the conservation of energy. We'll be using that idea here. Are you all with me? Are you all following? Are you all with me, students?
Yes, sir.
Are you all following? So the distance between the two electrons is given to be 2 meters. Okay, this is given to be 2 meters. Now, another electron from somewhere here is given a velocity v, and when it comes to the midpoint, the velocity becomes 0 itself. Okay. Now this distance here, as I told you earlier, is very far away. Now very far away means that you can take d to be as infinity. So take this as the initial point, take this as the final point. Use conservation of energy now. Use conservation of energy. Now what do you get if you use conservation of energy is, initially you have only kinetic energy, which will be half m v square, where m is the mass of the electron. Okay. When it comes to final kinetic energy, it is 0 because it is coming to rest at the midpoint, and therefore velocity will become 0. So kf is 0. Ui, on the other hand, is at a faraway distance, and therefore this will be at infinity, and hence it is 0. When it comes to the final one, it is at this point. At this point, if you have an electron, what is the potential energy given by? It should be minus 2k e square by 1 meter, isn't it? 1 square is equal to 1 square. And therefore, I can now say from the conservation of energy here, ki here should be equal to uf, or half mv square should be equal to minus 2k e square by 1. So substitute for all the values and get the answer. So v square is what we want, will be equal to minus 4 e square k by m. So let us see if we can quickly simplify this and get the answer. So this is minus 4 into e square. Keep it like that. I'll tell you why. This is a k. K is 9 into 10 to the power 9 divided by mass. Mass of the electron is 9.1 into 10 to the power minus 31. Minus 31, isn't it? It is minus 31. So you take this up, it becomes plus. So this will be minus 4 into this 9.1 and 9, cancel it off. Not a big issue. We'll not be able to, we'll not be making big mistake there. So cancel this off. You have 4 e square into 10 to the power 40. This is your v square. So V therefore will be equal to minus 2 into, forget about this minus sign then, minus sign, okay, will be equal to 2e into 10 to the power 20, 10 to the power 20. Now look at it, students. What is the charge of the electron? Is 1.6 into 10 to the power minus 19 into 10 to the power 20. So therefore, this will be equal to 3.2 into 1. So that will be 32 meter per second. 32 meter per second. So the answer to this question, therefore, is, where is it? Is 32 meter per second. So it's a nice question on the conservation of energy part. So I'm going to my next slide, which will be showing you some more problems on this one. Distance between H and Cl ions in a HCl molecule is 1.28 angstroms. What will be the potential due to this dipole at a distance of 12, angstroms on the axis of the dipole? Oh, this is something that I have not told you. Please, again, enter this in your data sheet or your synopsis, where the potential due to a dipole is completely missed. The potential due to a dipole is going to be Kp cos theta by r square. This is the relation where theta is, I'll tell you what theta basically here is. If you consider a dipole like this and has a dipole moment P, then theta is the angle that this R makes with respect to P. Okay, this is what it is. The expression is then Kp cos theta by r square. Now, for a point on the axis, theta must be equal to 0. So the potential will be therefore equal to Kp by r square. So let us try to obtain this. Do we know how to find out P now? The distance is going to be 1.2 angstroms and H and Cl. So the charge on the H will be equal to that of E. On the Cl will be equal to minus E. So the charge here in this problem is going to be equal to be E. Then distance 2D is going to be 1.28 angstroms, 1.28 into 10 to the power minus 10. So what will be the dipole moment? Dipole moment is Q into 2D, isn't it? So that will be equal to E into 2D. Okay. Now let's substitute and get the expression for the potential now. So this will be therefore this will be 9 into 10 to the power 9. Dipole moment is E into 2D divided by R. R is given to be how much? What is the distance at which I have to find out? 12 angstroms. So will be equal to 12 angstroms. 12 into 10 to the power minus 10, the whole square. Don't forget this. So the potential will be equal to 9 into 10 to the power 9 into 1.6 into 10 to the power minus 19. All right, into 2 into D. D is how much? What is the value of D given to be? 1.28 angstroms. That's a nice number, okay? 1.28 into 10 to the power minus 10. Look at it. You will not have calculators in your examination, but you will have to still work out problems like this. So this becomes 144 into 10 to the power minus 20. Now take it up, simplify, and get the answer. So this will be 9 into 1.6 into, I can write this in fact as 1.44 and then make this as 10 to the power 18. 10 to the power 18. I'll tell you why I make it 1.44. Okay, 1.44 into this. Then you will have 10 to the power 14 go up. Then you get this to be plus 18. So minus 1 into 10 to the power minus 10 into 2 into 1.28 divided by 1.4. See, this is 1 za. This is like 0.9 za. Okay, this is like 0.9 za. So this is 1 za. This will be 10 za. So the potential therefore will be equal to 20 into 1.28 into 10 to the power minus 11 volt. Very, very, very small voltage. Okay. So the problem number 7 will be therefore equal to I forgot 1 10 to the power 9 here, right? 1 9 I have forgotten here. So I have to write 10 to the power 9 as well here. 10 to the power 9. 10 to the power 9. So this will be 10 to the power therefore minus 2. Simplify this and you get the answer to be equal to 0.13. 0.13 is the answer. 0.13 volt. So let's see if you have any answer very close to that. 0.13 is there, and therefore I choose this as the answer. Okay. Now for 8th one. 8th one is also an excellent problem. Okay. You have electric dipole moment of a system of 3 charges. 2 charges we know how to do. How do you find the dipole moment of 3 charges placed on the vertices of an equilateral triangle as shown in the figure? So there's one Q here, another Q here, another minus Q here. So this can now be understood as something like this. I have one charge here Q, and that minus 2, I will make this as 1 minus Q here and say that there's a dipole from say minus Q to plus Q, and there's one dipole here like this. Call it as P, one dipole here. And another one, that minus another minus Q, you can take it with the charge Q and then have another dipole here, which is equal to P. So there are 2 dipoles, as you can see, one pointing like this, the other one pointing in this way. Now, let us say that the length is given to be L, by the way. And since it's an equilateral triangle, this angle is given to be 60 degrees. 60 degrees. So I'll have, therefore, 2 dipoles, P here like this, and you consider the components in this way. Consider the components in this way. If I call this if this angle is 60 degree, if this angle is 60 degree here, so this basically will be now, this will also be making an angle of 60 degree, 30 degree with respect to this. 30 degree with respect to this. So I can say this is P cos theta. This will be P cos theta. Okay, this angle also is theta. Then I'll have P sin theta. Then I have P sin theta. P cos theta will cancel off. So what do you have is only P sin theta. And hence I can say that the net dipole moment will be equal to 2P sin theta. 2P sin theta. Now what will this 2P sin theta be? 2 into P. I want the value for P. P is Q into, because there's a charge Q, into L. That will be a dipole moment. And then you have sin theta. Sin theta is nothing but sin 30. What is sin 30? What is sin 30? Is root is half. I'm so sorry. It's half. Oh, I think I know where the mistake is. I'm so sorry. I'm so sorry. Okay. This total angle is 60 degree. I have taken this as no, this is the direction in which it's coming, right? This is the direction in which it's coming. So with respect to this, this angle will be 30 degree. I'm so sorry. This angle is 30 degree, and therefore this should be 60 degree. So the theta here is 60 degree, because look at it, this angle is 30, so this is 30 degree, and therefore this angle must be equal to 60 degree. I'm so sorry about it. So this should be 60. If it is 60, then it is root 3 by 2. 2 will cancel off, so it should be root 3 into QL. So the answer to the net dipole moment should be equal to root 3 QL. Which one will give you that root 3 QL is this, and therefore the answer should be the third one. And also look at it, the resultant is pointing in the downward direction. Downward direction is minus j cap, right? And therefore it should be minus j cap as well. So hence this seems to be the right answer. This seems to be the right answer. I'm sorry for taking the angle wrong there. I should have been a little more careful. Yeah. Ninth one is super. Okay, let's solve this. Ninth one, in fact, is a fantastic problem. Let's look at this. A charge Q is fixed at each of the point x equal to x0, 3x0, 5x0 up to infinity on x-axis, and Q minus Q is fixed at each of the point 2x0, 4x0, 6x0. Therefore, take the electric potential at point due to the charge Q at a distance r from it to be Q by 4 pi epsilon r. Okay. Then the potential at the origin due to the system of charges. So imagine this is the origin. Now what has been done at x0, I have fixed a charge of plus Q at x0. Next, at 2x0, I have fixed minus Q. Minus Q. This is a very important problem. Lot of times this question comes. So plus 3 again at 3x0. And then minus Q again at 4x0. Then I'll have plus Q again at 5x0. And so on and so forth. And it goes up to infinity. It goes up to infinity. I have to find out what is the potential of the origin. The potential of the origin is simple. Is kq by x0 minus kq by 2x0 plus kq by 3x0. And it will go on like this, okay, up to infinity. So I can now say that V should be equal to kq by x0 into 1 minus half plus 1 by 3 plus next one will be minus 1 by 4 plus 1 by 5 and so on and so forth up to infinity. Now what will be the sum of this? Sum of this. I hope you all know that this essentially can be written as ln of 1 plus 1. Ln of 1 plus 1, because it's basically, this is where your this thing is varying, and this can be written as 1 plus 1. And hence you get this to be kq ln 2 divided by x0. Divided by x0. Anyway, k is given to be 1 by 4 pi epsilon naught. So should be equal to q ln 2 by x0. By x0. So see whichever is the expression that you get as the proper one for this. Choose the option from that. It should be q ln 2 divided by 4 pi epsilon naught x0. So fourth one should be the right option. Okay. Let me stop with this. There are 3 more problems for you to solve. You can do that in the next class, or you can actually take it as a homework. Okay. I will also be sending the solution for them. We'll solve, in fact, try to see if we can solve the remaining questions in the next class and then take up capacitors. So the next topic for me will be capacitors. Okay, fine. Thank you all. Bye-bye.
Thank you, sir.